Hello, today we're going to talk about the mean value theorem for derivatives. So far, you've had two other video lessons while Ms. Currian has been out. Those have been on linear approximation and L'Hopital's rule. Those videos are obviously still available to you. You have those worksheets. There is a possible quiz, short quiz for you guys at the start of class either tomorrow or Wednesday of this week on those two topics. So go back, look at the videos again, take a quick refresher, and make sure that you understand the concepts and how to answer questions like the ones that were posted in the video for a short quiz tomorrow. It would not be the whole period or Wednesday. It would just be a few minutes at the start of class. All right, so let's talk about the mean value theorem. The things you're going to need to know for today are the average rate of change of a function on an interval, the instantaneous rate of change at a point, how to use a theorem in a question, that's more of an overview of theorem questions, and the intermediate value theorem for continuous functions. You should have learned that already. So average rate of change of a function is simply the slope of the secant line that intersects 2 points on the function. On that interval from a to b, the points would be a comma f of a and b comma f of b. And if you just wrote a simple slope formula, that is the average rate of change of f of x on that interval. That's it, slope of the secant line. As opposed to the instantaneous rate of change at a specific x value at 1 point, at an instant, that's the slope of the tangent line to f of x at that point. And you should know very well already at this stage of the game that the slope of the tangent line in calculus is the derivative. So this is f prime of c. Those two things, average rate of change and instantaneous rate of change, are absolutely necessary for you to understand the mean value theorem for derivatives. All right, so in general, to use a theorem in a question, well, theorems aren't always, but they can be. They must be able to be written as a conditional statement. That's an if-then statement. So if A is true, then B will also be true. A could be one thing, it could be a few things that have to be true. We call those the conditions or the hypothesis of the theorem. And if they're true, then you have the conclusion. B would be the conclusion of the theorem. That must be true as well. So for you to use a theorem in a question, to use a theorem to prove something is true, it really takes 3 parts that you have to include in your answer. The first part is you have to write a sentence saying that the conditions for the theorem to be used are true so that you're allowed to use it. The theorem applies because these conditions are true. Then you show the work involved in the conclusion. So there'll be some sort of conclusion formula or statement, and you're usually going to be substituting some values in just to show that the conclusion that's stated in the theorem is going to hold up. And the last thing is just writing a conclusion sentence, something along the lines of, therefore, this theorem proves or guarantees that this conclusion, B, must happen. That's the idea, okay? The last thing is the intermediate value theorem for continuous functions. I'm not going to spend a lot of time on this. I'm just going to give you a quick overview. All right, if you got a function that's continuous on an interval and you have a starting y value and an ending y value, then you're going to hit every single y value in between those two. Now, let me erase these ones down here. I can't guarantee that I'm going to hit y values that are outside of that interval, but I can guarantee by the theorem that I'm going to hit y values that are in between the two. That's the idea. All right, and again, notice this was not stated as a conditional statement, but it could be. I could restate this as if a function f of x is continuous on the closed interval from a to b, then it takes on every value between f of a and f of b. Right? Every theorem can be written or rewritten as a conditional statement. So on your worksheet packet for today, here's the mean value theorem. I've written the whole thing out for you. The only thing that I'd like you guys to add is a little graph on the side there. So let me just show you what I've done first. I put a little f of x continuous function on an interval from a to b, and I'm going to draw a secant line through the endpoints there. All right? So the mean value theorem has two conditions. if your function is continuous on a closed interval from a to b, and also differentiable on the open interval, then there's going to be this conclusion that happens. But let's just talk about the conditions for a second. To be continuous on the closed interval means there's no holes in the graph, there's no gaps or discontinuities, no vertical asymptotes. You can draw the whole thing without lifting your pen or pencil up on the entire span from A all the way to B. That's the first condition. The differentiable part, a real easy way to think about that is when you look at the graph on the interval from A to B, there's no sharp corners or cusp pieces. A cusp is where two curved pieces come together. A corner is where two linear pieces come together. All right? So if it's continuous, you can draw it without lifting up off the page, and differentiable, there's no sharp corners or cusps, then we get this conclusion. And the conclusion is that you can see this formula here, f prime of c equals f of b minus f of a over b minus a. And what that really means is that the instantaneous rate of change, or the slope of the tangent line, has to be equal to the slope of the secant line at least one place, right? Slope of the tangent is equal to the slope of this secant line connecting the endpoints there. At least one place. It possibly could be many places. In the example that we just drew, it actually will be in more than one place. If you see, I would have a tangent line that's parallel to the secant line there, right? Parallel lines have equal slopes, so f prime of c, that's the slope of the dotted line, would be equal to f of b minus f of a over b minus a, the slope of the solid blue line. There's a second place on this interval from a to b that would happen, and that would be down there. And again, visually, spot this out, that the tangent lines are parallel to the secant lines through the endpoints. All right, that means that the slope of the tangent line, f prime of c, is equal to the slope of the secant line. So just to recap before we use this, the conditions for the mean value theorem are that the function has to be continuous on the closed interval from a to b, must be differentiable on the open interval from a to b, and if those two things are true, then the conclusion is that there has to be at least one place in the interval, one x value, where the slope of the tangent line to the function is equal to the slope of the secant line through the endpoints. That's the idea. So let's do a couple of questions, and then that should set you up fairly well for you to handle the rest of the questions on the worksheet. Here we go. Using this function, f of x equals negative x squared plus 3x plus 10, on the interval from 2 to 6, the closed interval, square brackets, closed interval, what is the average rate of change? So they're kind of setting up a mean value theorem question without saying it yet. All right, average rate of change is the slope of the secant, so we would need f of 6 minus f of 2 over 6 minus 2. And if you actually substitute 6 and 2 into the function rule, you get those values, and then you just simplify this fraction, and we wind up with an average rate of change of negative 5. Okay? Now, part B, on the interval from 2 to 6, they say open interval now, when does the instantaneous rate of change equal the average rate of change? Now, this is going to be fairly common, especially on the AP exam. They're going to ask you to use a theorem in a question without ever telling you the name of the theorem or which theorem it is that you have to be applying to the specific problem. When they say the instantaneous rate of change is equal to the average rate of change, that's the conclusion of the mean value theorem that you're supposed to know. So you should know that you're applying the mean value theorem here. So f prime of x is going to equal negative 2x plus 3. Right? There's going to be some x value on that interval, we'll call it c, where the derivative or the slope of the tangent line is equal to the average rate of change or the slope of the secant line. That's the negative 5. So I'm just solving this equation, and I wind up with c equals 4. Now, there's something we left out here. Because this is really a theorem question that you're applying, you really should be following those 3 steps. Why are you allowed to use the theorem? Show the work involved in the conclusion of the theorem. And then 3, write a conclusion sentence. So here I would say, since f of x is a polynomial, it is both continuous and differentiable on the interval from 2 to 6, and the mean value theorem applies. Then we would do the work that we just did here and up here, and then we'd write a conclusion sentence. Therefore, the mean value theorem guarantees that at one point, or at c equals 4, on that interval, by the way, you need to check whether that's in the interval from 2 to 6 there, okay? Let me just go there, right? Okay. On that interval, the c value of 4 guarantees that the slope of the tangent line is equal to the slope of the secant line, or the instantaneous rate of change is equal to the average rate of change. So kind of close to the intermediate value theorem. A lot of times they're mixed together in the same question. You got to know when to pick one over the other, and there's some real easy clues there. Here's a quick summary of the two, but for our purposes, we're really more concerned is when you choose one over the other. So if you're given a function on a closed interval, and then they ask you to prove that the rate of change or the derivative of that function is equal to some specific number, that's going to be a mean value theorem application. But very similar to that, for the intermediate value theorem, if they give you the same f of x function on a closed interval, and then they ask you to prove that the function they gave you, not the derivative of the function, but the function they gave you is equal to a specific value, that's going to be intermediate value theorem. Right? There's only one condition for the intermediate value theorem, that is that the function has to be continuous on your closed interval. All right, so let's look at a question where these things are mixed together, and we'll use these kind of little simple shortcut rules to pick which one is the appropriate one to pick. Here we go. This is on your worksheet as well. A hot air balloon launched into the air with a human pilot. Twice differentiable function h models the balloon's height measured in feet at time t, which is measured in minutes. And then the table above gives values for the height at specific times t. All right, part A, on the interval from 5 to 15. And by the way, it has the or equal to sign, so it's a closed interval. Must there be a time t when the balloon is 50 feet in the air? All right. Does there have to be a time when the balloon has a height of 50 feet? So think about this. They gave me the height, and they're asking me to prove that the balloon is at a specific height, right? Not the derivative of the height, at a specific height at some time on this interval. They gave me a function. They want me to prove the function's equal to a specific value. This is going to be intermediate value theorem. All right? So all theorems, 3 parts to the answer. State why you're allowed to use it, right? State the work shown in the conclusion, and then write a conclusion sentence. So part 1, why are we allowed to use this? Well, since our function is differentiable, it's also continuous, and the intermediate value theorem applies. Part 1. Part 2, for the intermediate value theorem, you got to show the y value at the start of your interval and the y value at the end of your interval, in this case, 40 and 70. And then the conclusion says, right, there has to be every y value that gets touched in between 40 and 70. You have to hit every y value if it's a continuous function. They're asking us to prove that the height is 50 at some point. Since 50 falls in between 40 and 70, this works out. And then we go to part 3, our conclusion sentence. Therefore, the intermediate value theorem guarantees there must be a time t when the balloon is 50 feet in the air. That's the idea. And just a little note here, when you write out your answer, use the exact words of the question. Right, see how I said there must be a time t when the balloon is 50 feet in the air? That was just copying the exact wording of the question. Use the words of the question to answer the question. All right, for part B now, again, on a closed interval, slightly different this time, we're from 20 to 30. Must there be a time t when the balloon's velocity is 1.5 feet per minute? All right, again, they're very, very good with the College Board questions at masking what it is that they're asking you, and you have to be really good at deciphering the clues. when they say the balloon's velocity there, they're talking about the rate of change of the height. All right? So we're going to go to our theorem now. This is going to be the mean value theorem. Since h of t is differentiable on the given interval, it is also continuous, and the mean value theorem applies. I'm going to backtrack just for a second. They want you to prove the rate of change, or the velocity, is equal to a specific number. They gave you h, and they want you to prove that h prime, that would be the velocity, is equal to 1.5 feet. When they give you a function and ask you to prove the derivative is equal to something, that's the mean value theorem. All right, again, velocity is the rate of change of the height, and that's h prime. Okay, so now I'm going to show my work involved in the conclusion. That's that the derivative, or the instantaneous rate of change, at some point, in this case on the interval from 20 to 30, equals the slope of the secant line. So the real work that we do here is just finding the slope of the secant line. So I set up the formula there. I go to the table and I substitute in my values for h of 30 and h of 20. And when I work that out, I get 1.5, which is exactly the value they wanted us to prove. They wanted us to prove the derivative, or rate of change, had to be 1.5 on this interval. And since the mean value theorem applies, it worked out. We just have to write a conclusion. Therefore, the mean value theorem guarantees there must be a time on the interval from 20 to 30 when the balloon's velocity is 1.5 feet per minute. I should make that an O. Balloon. Okay, there we go. So guys, that's the mean value theorem. It's often mixed, as I said, with the intermediate value theorem. Just follow those rules from before, and you should be able to handle this fairly well. When they give you the function and ask you to prove the derivative of the function's equal to something, mean value theorem. When they give you the function and ask you to prove that the actual function they gave you is equal to something on a specific interval, that's the intermediate value theorem. All right, if you have any questions, you can email me at any time or find me during the day, and I would be happy to help out. Good luck, and complete all the questions on the worksheet for homework. Have a good day.